back, everybody. This is a lesson for 7.7, General Factoring Strategies, and it's our last lesson in Chapter 7. So you will be doing a chapter review and a test this week as well. But let's go ahead and jump in. So again, these are just general factoring strategies. And remember, and I try and put this on all of your notes. By the way, if you're watching this video, I highly recommend either stopping and printing this out, or because it's only this one page with these 3 problems, you can just do it on a blank piece of paper or lined piece of paper if you would like. But we're going to be going over these 3 example problems here from the book on page 245. So first things first, remember when you are factoring, always begin by checking for and factoring out any common monomials before you go into the actual factoring. And then another thing that you want to do is see if any of them are going to have shortcuts. The shortcuts would be from lesson 7.6 that we did, and trying to determine, can I see any shortcuts there? So there's a list of some factoring tips in your book. There are 5 of them. So we're just going to go through these 3 problems here and try and go through those. So first thing here on A, what can you factor out of this? So in other words, what we were saying in like everyday terms, what do they all have in common? So I'm looking at these 3 right here, and they all have an X. So if you remember back to lesson 7.1, where we were pulling out greatest common factors. So we were pulling out the numerical greatest common factor, and we were pulling out the variable or the number greatest common factor. So in here, they all contain a 3. This has, you can factor a 3 out of that. You can factor a 3 out of that and a 3 out of that. They also all have an X. So we are going to first factor out a 3x. Now, if you remember from the last lesson that I had, I told you I was highlighting because that's going to end up being part of your answer, and you don't want to forget that. So I highlight it so it stands out and you remember, oh yeah, put that in the problem when you're done. So if we're going to factor out a 3x from all of them, we're essentially dividing each by 3x. So I'm just going to do that because then that helps you to know what goes inside the parentheses. So because of this, we'd have a 2. And if you recall, on when you are dividing exponents, you subtract. So that's a 3, that would be a 1. So it's going to be a 2x squared plus x, because the 3's cancel out. 2 minus a 1 would be a 1. And then minus 6. So there we go. So we've got some things that we can do there. And then what we're going to do, the next thing that we're going to do, once we've factored this out, then with this right here, we're going to apply the factoring method based on our terms here. So we're looking at 2 and a 6, because remember we do A times C. And in this case, A would be 6 and C, oh no, sorry, 2. Forgot that I factored that right out. A 2 and a 6, which equals 12. So we're looking for the factors of 12 that are going to give us this middle number or this middle term in the trinomial, which, you know, if there's, it's like an invisible 1. So we're looking for a 1. So I'm thinking of factors of 12 that are going to give me 1 when I add them up. So I can do, I already know minus 3 and a 4 is going to give me, and this is I did not mark this, but it's actually negative 12, and that is very important because it's minus 6, so it's minus 6 here, or negative 6 here. So this gives me negative 3 times 4 would give me a negative 12. And remember, if this multiplication symbol throws you off, then just use a comma. You know those 2 factors will equal negative 12. Also a positive 3 and a negative 4. So both of those are going to yield negative 12. One of them is going to give us a plus 1. So in this one, we would have 1. In this one, we would have negative 1. So that means we are using these two right here, a -3 and a 4. So then we're going to keep this 3x on the outside. And then we're going to start putting in our first 2x squared. Remember in our FOIL. Our last is -6. I'm going to have to write real small. I didn't give a whole lot of room here. So maybe it is better if you write these on a separate piece of paper. And then we have a -3x and a +4x. And then this was the L, the last one, -6. So then what we're going to do is group them. We're going to factor them by grouping them. Now remember, I'm keeping this 3x on the outside the whole time. If I need to cross this off and move it down, I'm going to do so it doesn't get in the way as we're taking notes here. So I'm taking these two and these two, and I'm going to factor those. So the 3x goes on the outside. And then what can I factor out of 2x squared and 3x? There's no number there that I can factor out. So I'm going to just factor out an x. And since I'm going to be having all kinds of commas and things in here, I'm going to go ahead and put the brackets. So if I factor an x out of here, messed up on that one. If I factor an x out of there, then I've got a 2x -3. Plus, then what am I going to factor out of those two? I'm going to factor out a 2, which gives me a 2x -3. So I factored out a 2 out of each of those. So if you go back and check, x times 2x gives you 2x squared. X times -3 gives you -3x. And same thing, distributive property, 4x -6. So then I can factor the 2x -3, but remember I got to keep this 3x on the outside. They both have the 2x -3 in common. And I'm left with x plus 2. And that is your answer. Yeah, I think we'll definitely have to rewrite that problem there. So this is your answer right here. 3x on the outside, because remember we factored that out. We just have to keep on factoring, make sure that it stays on the outside so that it ends up in our answer here. And then we have 2x -3 and x plus 2. Okay, let's go to this one. And I think I'm just going to move it right over here. So I have plenty of room to go down, and then I can go back over here. So x to the third power minus 4x squared minus 9x plus 36. Now, I don't know if you noticed the way that I'm writing this. I'm leaving lots of space in between because I want to very clearly see everything that's in the problem here. I need to make sure that I can see all of this. Okay, so we look at our problem here. This polynomial, it's got 4 terms here, so it's a polynomial. And we look to see if there are any common monomials, and there are none. They don't all have an x. They don't all have a number in common other than 1, obviously, because there's that invisible 1 right there. So there's nothing that we can factor out of there. So then we're just going to apply the correct factoring method based on the terms, and since there are 4, we're doing that grouping, right? We're going to factor by grouping. So if we take x to the third minus 4x squared, and then we have minus 9x plus 36. And then we're going to factor those 2 out. So we look at these, what do they have in common that we can factor out? And they both have an x squared. So if I factor out an x squared, remember it's just like dividing both by an x squared. I'm going to move this down a little. This is why I use pencil, hint, hint, to some of you. This becomes x minus 4. And then on this one, they don't both have an x, but within this 9 and this 36, or this negative 9 and 36, I can factor out a negative 9 because negative 9, first of all, I don't want to have the negative in there, so that's why I'm factoring out a negative. And the greatest common factor of 9 and 36 is 9. So I'm factoring out a negative 9 out of each. So that's going to leave me with x minus 4. And then what do these two have in common? It's that x minus 4. And you're left with x squared minus 9. Now, some of you might think, oh, we're done, but we're not, because look, we have the x squared minus 9. Do you remember your notes from when we were in lesson 7.6 and we had the difference of squares where it looked like this? And if you recall, the instructions or the kind of checklist that you have on this one is, by the way, this is simplified as far as it can go. So x minus 4 is going to stay there as the answer. But we still need to factor that one because we have x squared minus 9. Now, our two things that we needed to do a checkoff list to see, because I recognize this as a difference of squares. So we are determining if it has the operation between them is subtraction. Okay, check. And then also, are both of these terms perfect squares? So remember how we did x squared, and the perfect square of that would be x, and then 9. And the perfect square of that would be 3. So then this was our answer. And if you recall from lesson 7.6, which you may need to take your notes out, when you get that, the difference of squares, they're conjugates. So they're exactly the same except for the sign. So I'm just covering that up so you can see it. So x squared minus 9 really comes and is that answer, but we have to continue the answer down. So this big, huge, long thing, which I'm glad I moved the problem over here so I could write largely for you, this is the answer to this problem. So we had our difference of squares here, so we were able to factor it. You may get to the point where you don't even need to do this part because you can do this part in your head, and I'm okay with that. If you can go straight from x squared minus 9 to these two right here, then that's fine. You don't have to show this work for me. You could go straight from here to here. But sometimes you need to see it. For those of you that are struggling with it, you may need to see it because you know the pattern that when you do it, this is your answer. X and 3. So x plus 3 and x minus 3. Because remember, this is the F of FOIL, this is the L. The O and the I together end up canceling each other out. Okay, and then let's move to the last one here. So we have 3x squared plus 5x plus 1. And I'm going to attempt to just do the problem right down here. Kind of draw a little line so I can see the difference between the two. So first thing, we always remember to look for being able to factor out something. We cannot factor anything out of this problem right here. There's no common monomial. So we're going to apply the correct factoring method based on the number of terms. There are 3 terms. By the way, notice this. There's a squared, but there's 2 terms. So you look to see, can you simplify that and factor it out even more? This one, binomial, but you couldn't factor anything out because there's an x squared and a 9, which could produce a perfect square. Then that's why you were able to factor that even more and simplify it even more. But on this problem right here, there's no common monomial. It is a trinomial, so we're going to do the correct factoring method. So we're going to do the A and the C. And in that case, it's a 3 and a 1 because remember, this is ax squared plus bx plus c. So that's how you get the A and the C. The A goes with the number that is in front here. The C goes with the number here. So 3 times 1 equals 3. So, and because it's positive, you would have 1 and 3, or a -1 and a -3. Those are the only factors. This is a prime number. Those are the only set of factors or factor pairs that would give you a +3. So now we need to look at these two and determine, when I add them, can I get a +5? So when I add these, I get a 4. When I add these, I get a -4. I need to be able to add those to get a 5. If I can't, this is marked as prime. And that is your answer. So if you get to this point and you can't do it, double check to make sure that you've done all the correct factor pairs with it. And after double checking, if you have done all the correct factoring pairs and nothing equals a +5, +5, then your answer is just prime. There's no sense in continuing to work out all the factor pairs. And you could probably even do some of this in your head. 3, 1 and 3 are the only factoring pairs that will equal when you multiply A and C. And 3 and 1 are either going to give you 4 or -4. So that won't work here. So that is it for the last lesson of chapter 7. You are going to move to the chapter review, which I've listed in your suggested problems to complete. If you have any questions, please reach out, and good luck. Well, we made it. We made it to chapter 8. Can you believe it? I think this book only has 12 chapters, I'm pretty sure. 12 chapters. You know what that means. 5 chapters more. So let's keep powering through on this. We are on chapter 8, radicals. Now, I'm going to be honest with you. For some, this may seem totally simple. For others, it's going to take a little extra brain power on this. So just go in knowing this could be hard. This could be hard for me, and I'm just going to work because, you know what? Not everything in life is easy. And you get lots of rewards when something is hard and you're able to accomplish it. So stay positive, and let's see if we can't get through this chapter together. So today we're only doing lesson 8.1. It's just an introduction to radicals. So there's several different parts on here. I do recommend, if you haven't printed out your notes, just stop, go back to Canvas and print out your notes so that you can follow along with me on here. The very first thing, we're going to talk about the components of radical expressions. Now, I've already been writing things like this, and I know you've already covered this. Before you got to algebra, you've covered things like this called the square root. So every number is the product of two identical factors. Now, the square root of a number is the factor that, when multiplied by itself, equals the original number. So here's an example. 5 squared is 25. So that means the square root of 25 is 5. So we have something right here called the radical sign. And then I want to also, so here's your example, how you would write it. The radical sign with 25 inside equals 5. But let's go ahead and label this because each of these has a different name. This right here is what we refer to as the radical symbol. And then you have this number inside this little radical symbol, which is called the radicand. Radicand with a D. And then you have this number right here, which is called the index. So there you go. So that's the number, and that's going to determine which root you're taking. So for example, here, when no number is here, it's like there's an invisible 2. In fact, even my pencil makes it look invisible. So when you just see the plain radical sign like that, there's like an invisible 2 out there. So no number means there's a 2, and you're just, what number can I multiply by itself to get whatever number is in here? Now, this is also considered, just remembering from chapter 7, the end of chapter 7, we talked about perfect squares. This would be a perfect square. Now, if I had 26 in there, yes, you can find two identical factors that when multiplied will be 26, but they will not be whole numbers. So they're not going to be a perfect square. A perfect square is going to be when you don't have any decimals or fractions left over in it. Now, notice the index in the sample that we just wrote is a 3. So that's going to be a cube. That would be cubed. So this would mean what number, when multiplied by itself 3 times, will give me 125. And we're going to move on to that also, but I just wanted to go over that with you. Okay, so we jump into perfect squares and cubes, and I kind of just touched on that for you. A perfect square is a number whose square root is an integer. 25 is a perfect square because, that's just a little shortcut symbol for because 5 times 5 is 25. So is 24 a perfect square? Is there any number that we can, whole number that we can multiply by itself to get 24? The answer is no. And then what about 16? So think about what number could we multiply by itself to get 16? And it would be 4. So yes, 16 is a perfect square because you've got that equals 16. Remember from our last notes, let me see if I can find it. Here we go. Remember when I wrote this out? These are all perfect squares. The radical, 4, radicand, because it's 2. So if you think of it 2, 3, 4, 5, 6, 7, 8, 9, 10, you could even go 11 and 12, and you could have yourself a little like cheat sheet like this in case you come across numbers and you think, is that a perfect square? You'd have like a little cheat sheet already made out. So feel free to do this. If you're going to make a cheat sheet, I'd just go all the way up to like 15 if I were you. I only went to 10 here. But these are going to be the orders. And it's 2 times 2, 3 times 3. This is 7 times 7. This is 8 times 8, 9 times 9. Okay, so that's what makes it a perfect square. A perfect cube is a number whose cube root is an integer. So 125 is a perfect cube because 5 times 5 times 5 equals 125. So if we wrote it out like this, like the one that we had up here, the answer would be 5. And the reason is because 5 times 5 times 5 equals 125. It has to be 3 times because our index is a 3. So what number multiplied by itself 3 times will give you 125 in this case. Now do not be confused and do 5 times 3. Say there's 3 5s, so 5 times 3 is 15. Do not do that. That's not what we're doing here, okay? One thing I want to point out with the principal roots, if you look in your book, you'll see this section here for perfect squares and perfect cubes. So 2 cubed is 8, so it looks, the cube root looks like this. 3 cubed is 27, so it would be written like this. 27 cubed, or the cubed root of 3. Just like these are the square root of 4, square root, square root. There's, remember I said there was that like invisible 2 there. So this is what number multiplied by itself 3 times will give you 8. What number multiplied by itself 3 times will give you 27, and it's 3. Okay, let's move into principal roots here. So while it's true that 2 squared is 4, and negative 2 squared is also 4, when we're doing the square root of 4, it's only equal to 2. So the square root of 4, just written just like this, is only equal to 2 rather than it being equal to both 2 and negative 2. So the radical symbol indicates that only the principal root should be found. That means the root that matches the radicand in the sign. And remember, this is the radicand. In this case, it's 4. In this one, the radicand is 125. So just to remind you what radicand means. So to indicate a negative value, you need to put a negative sign in front of the radicand. So let's do an example so you can see what it looks like. So you've got the square root of 4 is 2, sorry, not 4. It's a positive 2 only. If you want it to be a negative 2, then you put a negative outside of that radical symbol, and then you'll get negative 2. You might even see this, plus or minus square root of 4, which means that your answer would be either plus or minus 2, meaning positive or negative 2. So that's going to be what the principal roots are. Principal roots are the ones that should be found. They're going to be positive unless there is a sign outside of this. So now let's look at approximating irrationals. So when you have these perfect squares, 25 and 36, they're, remember from, I think it's lesson 1.1, rational and irrational numbers. These are both rational numbers because they're perfect squares. If you get a root like 30, it's irrational. Because remember, the decimal expansion of an irrational number neither terminates nor repeats. And so with this, there's no whole number that you can multiply by itself. In other words, a perfect square. There's no perfect square for 30. So what you can do sometimes with math is you can find out where would it be, what would the value be. It's going to fall between two different rational numbers. So let's go ahead and look at an example here. So if we have the square root of 30, I want you to think back or look at your cheat sheet of this right here. So if we're going to have 30 here, where would 30 fall in between here? 30 would fall right here in between these two, right? So it's going to fall in between the square root of 25 and the square root of 36. So again, I'm going to show you. We have square root of 30. Where would 30 fit in? It would fit in right here, in between the square root of 25 and the square root of 36. Do you see why having this little cheat sheet here would be really nice? Because then that shows you right there without you having to, do a whole bunch of extra brain power here. You already have it written down. And if you make a cheat sheet like this, I'm totally fine with you using it on the test, by the way. So something that would be helpful for you. So 30 is going to fit in right here. So that means for our perfect squares, we would do the square root of 25 and the square root of 36. Now I'm going to add just this really small, because I probably should have done that a little bit bigger there. So the square root of 30 is going to be bigger than the square root of 25, but it's also less than the square root of 36. Now, what is the square root of 25? Is 5. And the square root of 36 is 6. So the square root of 30 falls somewhere in between 5 and 6. And this would be your answer. And if, let's see, I don't know if I can, I'm going to see if I can real quickly show you this. So if I were to type in, just so you can see what the number is, we're going to test it out here. So that means it's going to fall, it would be some number with a decimal or fraction. I'm going to go with decimal here since I'm using a calculator. It's going to fall somewhere between 5 and 6. So just to show you, plug in 25. This is how you use it, by the way. And then you plug in this. Do you see how it has the square root sign? And it even has the 2. And then you hit equal. You get 5. Okay, so let's do 36 also. Okay, I like this new update, by the way, with Apple, because it shows you what you actually typed in. Now let's go ahead and do 30. So if we do 30 and we do the square root of that, we get 5.477. So that fits in with our answer here, because the square root of 30, obviously it's not a perfect square because it's got a decimal. That's why it's irrational. An irrational number. So, so the answer falls somewhere between 5 and 6 at 5.477, like that. So that's approximating irrational numbers. So when you have to say, okay, well, this is irrational, but like approximately where would it be? Well, it's going to be between 5 and 6. It's greater than 5, then less than 6. So let's look at the fractional exponents that we have here. And fractional exponents may be used to express a radical without using a radical symbol, which sounds kind of strange, I'm sure. But when you look at this, you've got the square root of 2 to the 6th power. Now, for this problem, I'm going to go ahead and write in this 2, and you might want to write that in also. Now, when you see the radical sign, if there's no number there, remember you automatically assume there's a 2 there, because it's the square root of, so squared 2, as opposed to cubed or a 4, as we'll get into later. So, sorry, that's my dog barking. So then you can see how you would write it. Okay, I'm back with hopefully no more dog barking interruptions. Sorry about that. So I wanted to show you, if writing it with a fractional exponent is how you would write this. So if you're going to write a radical, express a radical, but you're not going to use the radical symbol, then you're going to write it with a fractional exponent. So you can see the exponent inside the radical symbol, so as part of the radicand, is the numerator, and then the index is the denominator down here. So if I were to write the cubed root of 13, which is going to be an irrational number, by the way, but if we were going to write it as a fractional piece, then we would, or exponent, we would write it like this. So 13, and then it would be 1/3. And you're probably saying, well, where'd you get that 1 from? Because this is just 13 to the first power. There's no exponent here. There's no exponent there. We assume that's just a 1. Okay, then what about the cubed root of x squared? See if you can do this one by yourself based on these two examples that we've done here. So we take our radicand, then we take our exponent and our index, and you express it as a fraction. So this is fractional exponents. This is your exponent, and it's in a fraction. So that's why it's called a fractional exponent. And that's how you can express a radical without using this radical sign. So what if we worked backwards and we did 16 1/2? So if you're going to work backwards here, so you know 16 is going to be the radicand. So let's do a radical symbol. We know 16 is going in here. That top number, and if you forget, look at your example. 6, oh yeah, that was the exponent. So you don't need to write a 1 there. It's assumed there's a 1 there. And then your numerator was the number outside. And in here it's a 2, and you don't even need to write that because it's assumed there's a 2 out there because this is the radical symbol, the square root symbol. Okay, let's go ahead and move to the next section, which is doing a couple of samples together. So what we're going to do on here is we're going to express these 3 as fractional exponents, and then we're going to simplify, and you'll see what I mean by that. So you might want to have your notes out, because I might ask you to do some of these by yourself, and then we'll check them. So first we're going to express it as a fractional exponent. So we have our radicand, and then our exponent, and our index. Now this is what I mean by expressing using a fractional exponent. What I mean by simplifying is that fraction right there, 14/7, can be simplified. 14 divided by 7 is 2. So that means this becomes 6 squared. And that becomes 36. So this number right here is 36. So this is the answer. That's what I mean by simplify. If you have a fraction, you're going to simplify that fraction all the way down. And if you get to something like this, then you can simplify it even more. Okay, let's work on this one. So this becomes x, and then 18/6. We can simplify that fraction, so it ends up being x to the 3rd power. And that is your answer. Okay, not too terribly difficult. See if you can do C all by yourself. You can go ahead and pause it because I'm going to work through it. So we have n, exponent, index. Simplify that. And what that equals actually would be the square root of n. So pay attention to that. If it's a 1/2, you can actually simplify. Since a fraction is this 1/2 fraction, you would just express it as a radical. I don't know, you may not have gotten that one correct. You may have just stopped here and not realized that this would turn into this. This is the simplified version of that. Okay, well that is it for our very first lesson of 8.1. The rest of our lessons, Lord willing, will be in class. So if you need any help on these problems, please see me. And remember, don't forget about, if this is difficult for you and you need somebody else to explain it for you, you can always look on Khan Academy. And my suggestion is to look at what the title of our lesson is and type in Khan Academy. Then in the search bar, go ahead and type whatever the lesson is. Or you can just go to Algebra. I believe on Khan Academy you can go to Algebra and find this section of what it is, or look at radicals and see which lesson might apply to this. They're very short lessons and they're really helpful. So hopefully you don't need to, that I was able to explain it to you but well enough, but I know that sometimes you need somebody else. You know what? Actually, I just thought of something I want to go over with you just real quickly, because I want you to see, I'm going to actually do number 17. I just happened to look up in the book and saw this, and I thought maybe I should go over that type of problem with you. We did briefly touch on it, but remember what this would be. So you can just kind of cover that up for now, or you can just write it because you know the answer is going to be a negative because you have the negative on the outside. And then you do the square root of 36. I can't even remember if this is one of the problems I had you do, but I just kind of wanted to show you what to do for this. And so it would be 6, because the square root of 36 is 6. But remember, there was the negative on the outside, so you want to do that. So just a reminder, when you have that negative on the outside. Okay, and that is it. Let me know if you have any questions. Okay, just kidding. I thought of one more that I better show you because it didn't go over it, I don't think, in the notes, and you're going to come across this problem and not understand. So if you look in your book at number 12, after doing this one, I thought I better look and see if there are other ones they might struggle with. And this is going to be helpful for you because you may come across several of these. So your instructions on these type of problems read, write the value that would make each statement correct. If there are no real number values that would make the statement correct, write no real. So here we did have a number, it would be -6. But here, when you have a negative inside, when your radicand is a negative, that is going to be no real, because there is no real number value that would make this statement correct. What are we going to multiply by to get -16? Well, it's going to be a -4 times a 4. But those are two different numbers. One's a negative and one's a positive. And so that's why there's no real number. It's either going to be both negative like this, or both positive with no subtraction, a negative symbol there. So just a reminder for you on that. When the negative is inside with the radicand, your answer is no real. Okay, for reals, that is it.